The evolution of the outlier. Concept modern data science has revolutionized our way of understanding outliers, transforming them from simple errors to be eliminated into valuable sources of information. At the same time, Malcolm Gladwell's book, Outliers, the Story of Success, offers us a complementary perspective on human success as a statistically anomalous but meaningful phenomenon. From simple tools to sophisticated methods. In traditional statistics, outliers were identified using relatively simple methods, such as box plots, z-scores, which measure how much a value deviates from the average, and interquartile ranges, IQR. These methods, while useful, have significant limitations. A single outlier could completely distort a linear regression model. For example, increasing the slope from 2 to 10. This makes traditional statistical models vulnerable in real-world contexts. Machine learning has introduced more sophisticated approaches that overcome these limitations. Isolation forest, an algorithm that isolates outliers by building random decision trees. Outliers tend to be isolated more quickly than normal points, requiring fewer divisions. Local outlier factor. This method analyzes the local density around each point. A point in a region with low density compared to its neighbors is considered an outlier. Autoencoder, neural networks that learn to compress and reconstruct normal data. When a point is difficult to reconstruct, producing a high error, it is considered anomalous. Types of outliers in the real-world data science distinguishes different categories of outliers, each with unique implications. Global outliers, values that are clearly off-scale compared to the entire dataset, such as a temperature of 10°C recorded in a tropical climate. Contextual outliers, values that seem normal in general, but are anomalous in their specific context. For example, a purchase of $1,000 in a low-income neighborhood, or a sudden increase in web traffic at 3 in the morning. Collective outliers, groups of values that taken together show anomalous behavior. A classic example is synchronized peaks in network traffic that could indicate a cyber attack. The parallel with Gladwell's theory of success, 10,000-hour rule and its limits in his book. Gladwell introduces the famous 10,000-hour rule, claiming that expertise requires this specific amount of deliberate practice. He gives examples such as Bill Gates, who had privileged access to a computer terminal when he was still a teenager, accumulating precious hours of programming. This theory, while fascinating, has been criticized over time. As Paul McCartney noted, there are many bands that have done 10,000 hours of practice in Hamburg and have not been successful, so it is not a foolproof theory. The very concept behind this rule has been challenged by several authors and scholars, and we ourselves have strong doubts about the validity of the theory or its universality. For those interested in exploring the topics covered in the book, I recommend this example, but you can find many others if you are interested. Similarly, in data science, we have realized that it is not only the quantity of data that counts, but also its quality and context. An algorithm does not automatically become better with more data. Contextual understanding and appropriate quality are needed. The importance of cultural context, Gladwell, highlights how culture profoundly influences the probability of success. He discusses, for example, how the descendants of Asian rice farmers tend to excel in mathematics not for genetic reasons, but for linguistic and cultural factors. The Chinese numerical system is more intuitive and requires fewer syllables to pronounce the numbers. Rice cultivation, unlike Western agriculture, requires constant and meticulous improvement of existing techniques, rather than expansion into new terrain. This cultural observation resonates with the contextual approach to outliers in modern data science. Just as a value can be anomalous in one context, but normal in another, success is also deeply contextual. Mitigation strategies. What can we do? In modern data science, several strategies are used to manage outliers. Removal. Justified only for obvious errors, such as negative ages, but risky because it could eliminate important signals. Transformation. Techniques such as Windsorizing, replacing extreme values with less extreme values, preserve the data while reducing its distorting impact. Algorithmic selection, use models that are inherently robust to outliers, such as random forest, instead of linear regression. Generative repair, use of advanced techniques such as GANs, generative adversarial networks, to synthesize plausible replacements for outliers, real-world case studies on outlier detection in machine learning, and artificial intelligence. Recent applications of outlier and anomaly detection methodologies have radically transformed the way organizations identify unusual patterns in various industries. Banking and insurance. A particularly interesting case study concerns the application of outlier detection techniques based on reinforcement learning to analyze granular data reported by Dutch insurance companies and pension funds. Under the Solvency II and FTK regulatory frameworks, these financial institutions must submit large datasets that require careful validation. The researchers developed an ensemble approach that combines multiple outlier detection algorithms, including interquartile range analysis, nearest neighbor distance metrics, and local outlier factor calculations, enhanced with reinforcement learning to optimize the ensemble weights. 1. The system demonstrated significant improvements over traditional statistical methods, continuously refining its detection capabilities with each verified anomaly, making it particularly valuable for regulatory oversight, where verification costs are significant. This adaptive approach addressed the challenge of changing data patterns over time, maximizing the usefulness of previously verified anomalies to improve future detection accuracy. In another noteworthy implementation, a bank implemented an integrated anomaly detection system that combined historical data on customer behavior with advanced machine learning algorithms to identify potentially fraudulent transactions. The system monitored transaction patterns to detect deviations from established customer behavior, such as sudden geographical changes in activity or atypical spending volumes. 5. This implementation is particularly noteworthy as it exemplifies the shift from reactive to proactive fraud prevention. The UK financial sector has reportedly recovered about 18% of potential losses through similar real-time anomaly detection systems implemented across all banking operations. This approach allowed financial institutions to immediately block suspicious transactions while flagging accounts for further investigation, effectively preventing substantial financial losses before they materialized. 3. The researchers developed and evaluated a machine learning-based anomaly detection algorithm specifically designed for the validation of clinical research data across multiple neuroscience registries. The study demonstrated the effectiveness of the algorithm in identifying anomalous patterns in data arising from carelessness, systematic errors, or deliberate fabrication of values. 4. The researchers evaluated several distance metrics, finding that a combination of Canberra, Manhattan, and Mahalanobis distance calculations provided optimal performance. The implementation achieved a detection sensitivity of greater than 85% when validated against independent datasets, making it a valuable tool for maintaining data integrity in clinical research. This case illustrates how anomaly detection contributes to evidence-based medicine, ensuring the highest possible data quality in clinical trials and registries. 4. The system demonstrated its universal applicability, suggesting potential implementation in other electronic data capture (EDC) systems beyond those used in the original neuroscience registries. This adaptability highlights the transferability of well-designed anomaly detection approaches across different health data management platforms. Manufacturing. Manufacturing companies have implemented sophisticated computer vision-based anomaly detection systems to identify defects in manufactured parts. These systems examine thousands of similar components on production lines, using image recognition algorithms and machine learning models trained on large datasets containing both defective and non-defective examples. 3. The practical implementation of these systems represents significant progress compared to manual inspection processes. By detecting even the smallest deviations from established norms, these anomaly detection systems can identify potential defects that might otherwise go unnoticed. This capability is particularly critical in industries where component failure could lead to catastrophic results, such as aerospace manufacturing, where a single faulty part could potentially contribute to a plane crash. In addition to component inspection, manufacturers have extended anomaly detection to the machinery itself. In addition to component inspection, manufacturers have extended anomaly detection to the machinery itself. These implementations continuously monitor operating parameters such as engine temperature and fuel levels to identify potential malfunctions before they cause production disruptions or safety hazards. In organizations across industries have implemented deep learning-based anomaly detection systems to transform their approach to application performance management. Unlike traditional monitoring methods that react to problems after they